We can increase capacitance, which would be a good goal because we can then store more energy in the capacitor by inserting a dielectric into the gap between the two plates. Instead of just air, we're going to put in an insulator where it's a specific kind. The atoms in a dielectric, here are the atoms, they're slightly polarized. What that means is the electrons are not evenly distributed throughout the atom or molecule, whatever we're putting in here, so that one side will be a little more positive than the other and the other side will be a little more negative. They'll still be neutral. They'll just be this little shape where this side will be negative, this side will be positive. Before we charge the plates, if we just put the dielectric in here, the atoms, their plus and minuses, are all pointing in random directions. So as a group, the dielectric is unpolarized. Each atom is slightly polarized, but as a group, on average, you have a neutral dielectric here. You don't have one side more negative or more positive than the other. Now we apply a voltage to the two parallel plates. What's going to happen is we'll have a plus charge up here. This plate will be positive. Okay. This plate will be negative. What is that going to do to all the atoms in the dielectric? They're going to line up. You can see here the negative of this atom or molecule is more closely attracted to here. Same with this guy. The negative gets attracted to the top. So I have a polarization here now. All these little atoms line up. So if I have a positive here and a negative here, what does that look like? That looks like an electric field in that direction. So what have we created here? We have an internal electric field generated by the dielectric, and it opposes the applied electric field from the battery. The strength of this field is going to depend on the material of the dielectric, how polarized the atoms were in the beginning, and how easily they respond to an external field. So just quickly summarize, positive charges up here, they're going to attract the negative ends of the atoms or the molecules in the dielectric. They line up, and we will now have an electric field opposing the electric field from the capacitor. Vector diagrams are really cool. Let's see what happens. The blue line is the electric field of the plates without the dielectric. The dielectric now, the material got polarized and had an electric field going in the other direction, and typically it's smaller than the electric field of the plates without it. We now add these two electric fields together, and we have the electric field with the dielectric, or the net electric field, is smaller than it was in the beginning. So for a given applied voltage, the net electric field is smaller. This is very helpful for another reason, because if the electric field between the plates gets too big, you keep applying more voltage, the field gets very large, it could cause something called a dielectric breakdown in that space. A dielectric breakdown is very bad, because here's our two plates of the capacitor, and we talked earlier how you had a battery here. It would charge the capacitor, and all charge would flow through here. A dielectric breakdown means that this electric field is so powerful that charges, electrons, can now move through the gap, through either the dielectric or the air. That's known as a spark. That's how lightning works, or when you touch a doorknob after rubbing your feet on the carpet. Okay, lightning is a much bigger effect, but the same physics. So what we've done here is you have charge flowing where it shouldn't. That would destroy the capacitor. And also, if you were touching it or was near other circuit elements, it could harm them in addition. You're putting a lot of energy where it doesn't belong. You're getting a spark. This breaks, and people or equipment could get hurt. The dielectric material was originally neutral. Once it became polarized, more charge was now present. You had the charge on the plates, plus the charge induced in the dielectric by separating the charges positive and negative on either side of the material. Thus, the total charge in the capacitor increased. The voltage stayed the same, still connected to the same battery, so when we use the definition of capacitance, Charge went up, voltage stayed same, capacitance of the configuration increases. That enables you to store more charge for a given voltage, and you can store more energy. An engineering benefit to the dielectric is that it insulates the plates from each other, and thus the distance between them can be made very, very small, and charges will not flow between the plates, such as sparks, but will flow through the battery, and it will work properly. So one way to make a dielectric is take two plates, positive and negative, stick a dielectric in between them, then roll it up so you can have a cylinder, which is a more practical, smaller shape to store energy in. And the dielectric will prevent any sparks or charges going between the two plates. Every material has a dielectric constant, kappa. That's a Greek letter or little k. We have a sample table of values here on the right. For a vacuum, k equals 1. K air is about 1. It's close enough. And if you have a dielectric present, we told you how it would increase the capacitance. The same formula for capacitance works, but we just add the kappa in there. So let's see, asbestos here would have a greater capacitance than bakelite, which would have a greater capacitance than paper. So any of these dielectrics, when you insert them, you can store more charge and have a greater capacitance than if you had air between the plates. And just a little simple summary, the larger the value of K, the greater the capacitance.